Okay. All right. So let's do a little bit of revision on what we were talking about last week. Or we could do revision of any topic already if you want to start doing that.
Is midterm gonna cover the whole thing up to what we discussed last week?
Yes.
Then let's do a revision of basically.
Okay. If you like. What would you like to revise then?
I mean, let's go from like the fresh. We came off fresh to like all the way backwards.
Okay.
I think the new topic may be a little harder than the like. I think the math probably don't need to review, but like some calculation we might like.
Okay. I don't know. Like, so maybe could you choose a topic, like one of the slide sets, and then we could.
Okay.
Yeah. I mean, we still have one more lecture before the midterm, so.
We're gonna cover this lecture. Wait, the midterm is on.
Midterm is next week. Next week.
Oh, so we
Next
still
week
have,
today. Yeah.
So we still have 2 lectures.
Yeah, we still have 2 lectures.
Okay.
So we could do revision on, like,
Thursday.
on Thursday as well. Maybe,
Are we gonna one class or 2?
Huh?
Are we gonna do one section of revision or 2 sections of revision?
Well, it's sort of up to you, I guess. If you feel like you need 2 revision sessions, then I'm happy to do that. But I don't know. Yeah, it's up to you.
So the midterm will cover the first 12 chapters.
Yeah, basically whatever we've completed. Yeah,
Okay.
yeah. So we've done sort of about half of Composite Systems. So yeah, so it could be anything, including that. Yeah.
Okay.
So okay, do you want to? If you want to do revision, then why don't you choose a slide set?
So are we going to learn new things today?
I think it's up to you. So if you're sort of comfortable to, then I mean I was gonna continue on with this lecture, this 12, but if you feel like you want to do more revision, then you can do that too.
What do you think, Eve?
I think that we can do the revision on Thursday. So today we'll finish chapter 12.
Okay, all right.
Okay.
Okay, so why don't we then finish this one and then revision will start. Then
Okay.
it'll be a clean break, right? Okay, all right. So we were talking about composite systems, and basically, this is what happens when you have more than one quantum system together, right? So up until now, we were only talking about basically single quantum systems, and when I say multiple quantum systems, usually this means something like, there's more than one particle, so it could be like more than one atom. So instead of just having one atom with some number of levels, which I'm kind of drawing here, I could have 2 atoms, and they could form a single quantum system. Could be 2 photons, or 2 cats, or 2 anything really. So usually each quantum system is kind of defined by their kind of physical location and what they're made of. So this is, in this case, we've got Alice and Bob, and they each are in possession of a D-level system. So in general, you would write a quantum. Whoops. write a quantum state of the composite system together of Alice and Bob by basically all the different combinations of states that you could possibly have. So I've chosen an example here of 3 levels each, and there's a total of 9 possible states. So basically this now becomes like all the basis vectors in our kind of quantum system. And the way that you can sort of write this mathematically when you have 2 composite systems is this sort of tensor product symbol. So you sort of, basically what that means is you're combining 2 smaller vectors, and then you're making a bigger, well, it's not a bigger vector, but it's a vector in a bigger space, right? So the composite system lives in a 9-dimensional space. The original ones live in, say, deal with 3-dimensional spaces. So this takes 2 3-dimensional, like 2 vectors living in 3-dimensional space, and then it makes a new basis vector in this 9-dimensional space. And because I'm a physicist and I'm lazy, I don't want to write lots of notation. Often I just even omit this tensor product symbol, or even define a new vector with these 2 indices like this. Okay, so a general quantum state in this larger composite system is written like this. So these 9 combinations that we just had are, these are our basis vectors, and basically you can stick any coefficient you like in front of these basis vectors and make the superposition. So it just works simply as that, simple as that, and these coefficients have to be normalized as usual, just because it's a composite system. You still have to obey that normalization, and here are a couple of different ways of writing it. It's basically the same thing. So for 2 qubits, the 4 states would be like these 4 combinations, and you can have any coefficients in front of it, and you normalize it like this. For a special case of states, so this was a completely arbitrary 2-qubit system here, but you can have a particular class of states where basically the states are totally independent of each other, and it works a lot like independent probability distributions. So if you have 2 probability distributions and they're independent, then the probability distributions just sort of multiply. So if you have P1 and P2, then got 2 probability distributions, and they just multiply. So quantum mechanics works a lot like that. If you have 2 independent quantum states, essentially the states just sort of multiply in the sense of this tensor product. So here is sort of Alice's state, psi A, and his Bob's state, psi B, and the new quantum system is just the tensor product of those 2 states, and you can write this in a form that looks a lot like what we had before, except that you can already see that this coefficient here, this A and A and B and B, this coefficient here is actually more specific than the more general wave function that I wrote down, say over here, which was A and B. So you can write this one on this page as this one, but not the other way around. You can't write any wave function in this form. This is it's a more particular form. And how do you make measurements in this composite system? So actually all the things we've talked about up until now basically just carry over into this composite system language. So previously we were just saying, okay, if you're doing measurements, if you have a state like something like this, then you do a measurement, and then basically this collapses to this state, and the probability is the modulus squared of the coefficient. Basically, there's no difference here just because you have a composite system. Basically, instead of that, what we're going to have is this more general wave function with some more indices, NA and B, NA and B. And so basically, you're going to have like different outcomes like this. And so the probability is, well, so in this case this was 0. Here we've just got sort of more labels, because basically, this thing is still a basis vector. So it's a composite system, but it's actually, just a kind of a particular case of this, if you like, because these A's and B's, these form a new kind of space, right? So that means that if we're going to do a measurement on this composite system, basically the same thing applies, but usually what happens sort of in practice is that actually, because each of these composite systems, it has its own physical, let's say location. Alice holds this particle, Bob holds this particle. So often what happens is that actually the type of measurements are actually sort of local on each particle. So Alice has her own measurement device, Bob has his own one, and then so basically the composite measurement is actually just a combination of both Alice and Bob measuring. So naturally, in this case, you end up with all these different, say, all 4 combinations, just because Alice can get 2 outcomes, Bob can get 2 outcomes, and then 2 times 2 is 4, so you get basically all the 4 outcomes. If you just view, so you can view it as Alice and Bob just making separate measurements, or you can view like this whole Alice and Bob combined measurement system, measurement device, as consisting of these 2 individual measurement devices. Okay, and I think this is where we got up to before. So for the case of an independent state, because of, you have this sort of product kind of form, this works exactly sort of the same way as independent distribution. If you do a measurement on independent state here, so this is the independent, so it's just a product, then what happens is that actually, say if you wanted to look at the probability of Alice getting 0, then it's completely independent of whatever the state here is on Bob, because, calculation is here, so the probability of getting Alice's 0 for this combined kind of measurement, it has to be the probability of Alice getting 0, Bob getting 0, and then Alice getting 0 and Bob getting 1. So it has to be the sum of both of those cases, because both of those cases mean that Alice got 0. Right? So Alice getting 0 is equal to P00, P01. And then if we calculate probabilities of these 2, then it's A0, B0 squared, and A0, B1 squared. And then because you can factorize this, B0 squared plus B1 squared is 1, so it's actually independent of B. So there's no B's in here at all. So it's the same result as if this Bob's state wasn't there. So this kind of makes sense because actually, when we write down a quantum wave function, you could actually write down the wave function of all the, say all the particles in the universe, right? Like, I'm specifically interested in this particular atom here, but, well, there's a wave function of my table and then the clock and the room and everything, all the planets. In principle, you could include all those things, but actually they're all kind of irrelevant because of kind of this effect. So, because basically, all the planets and the room and the table, they might have a wave function, but it's in this product form, or should be in this product form. And they basically don't really affect the result of the thing that you're actually interested in, which is the atom, which might be the first one. So, so that's kind of the property of independent states. Okay, so I think that's where we got up to last week. Any questions on the revision part? No. Okay, so so let me talk a little bit about the other things that we've learned so far. I think I didn't include this in the slides which I uploaded, but I just added them now. But just for completeness, we've been talking about wave functions and in composite systems, and talked a little bit about measurements. But previously we were talking about observables and things like that. So I should tell you how those things work for composite systems. And the good news is that it's actually not really very different at all. So if you have some observables, so remember some general observable, so for just a single qubit system, single system, not a composite system, but just a single quantum system. If you remember, I was writing observables like R is equal to, okay, maybe I'll stick to the same. So remember, observables were defined according to some kind of matrix like this. And basically what this means actually in terms of the observable is that I'm going to make my measurements, measure in this M basis, and going to do my measurement in M basis. That means I'm going to get some probabilities, probability for basically outcome when we get the state M. And each time I get that, then I'm going to assign some value to it. So that's this R. And so basically the expectation value of R should be basically the probability of getting it times by the value, right? And that's, of course, how you define any kind of observable. And I told you that, well, what's convenient is to actually define this observable matrix thing. So R, just define it like this. And if you do that, then instead of sort of working it out kind of like in this way, what you can just do is work it out exactly by kind of sandwiching this R operator, which we just constructed, with the wave function, and this will always give the same answer. So it's what we had before. So for composite system, basically it works exactly the same way, except that all these M's, which were particular outcomes, are now got two labels, right? So instead of it having like instead of it just having M inside here, now I've got MA and B, because it's a composite system. We're going to, Alice is going to measure, Bob is going to measure, for example. So that's why we've got these two labels. And then, so basically everywhere that you had this M, you now have MA and MB because you've got like two labels because it's two composite system, two variables, right? And if you calculate expectation values, then what you'll find is exactly the same argument as you had before. If you substitute this R into this usual formula for expectation value, then what you'll get is something like this, where this is basically like the coefficients of the state, but rewritten in this M basis. So here it's in this N basis, which maybe it's a different basis to the M. So, and then so this is how you transform the coefficients, and then you put that in there. That's basically the probability, and R is just the values that you assign. So this formula is basically really just exactly that. So, it looks sort of more, it's like, oh, what's all these variables? But actually, it's exactly the same. I mean, all I've really done is just replace the M's by MA and B because now everything's got two variables. Okay. So that's for a general observable here. So here I just wrote a general observable R, right? So, but actually, as I said, usually what happens is that Alice is making a measurement and Bob is making a measurement, and so actually usually the observables are also kind of sort of independent to each other in the sense that you can assign values independently of each other's measurements. Okay. So, for example, so let's say Alice has got this observable S, right? So this is just defined on Alice's system. So this thing is just like here. Yeah. And let's say Bob is got this observable SB. Okay. And so we can make a joint observable between Alice and Bob. So what you do is, again, you do sort of a tensor product that, again, basically combines these vectors together to put it in the larger space. And so in this case, the observables are actually just you just multiply the observables from Alice and Bob. Okay. So if you just do tensor product of those two observables, then it basically corresponds to each of the values multiplied. So this is obviously a specific case of the more general observable because, again, this thing here, this coefficient, this SNA, SNB, is, of course, a more specific version than what you have for the general measurement. So all I'm basically saying here is that in general, for independent observables where Alice and Bob each make or have observables separately, then this has a particular form. Okay, might look a little bit abstract, so let's do a couple of examples. Okay, so this is basically how I sort of work it out. Even though I sort of wrote this kind of formula for this expectation value of R, actually, I don't really use that formula as such to work stuff out. In fact, you can just sort of work out these things more or less, just compute the expectation values by just evaluating these matrices multiplied by the states. Okay, so suppose you had a question like this. So suppose it was like, so evaluate expectation value of Z1, Z2. So Z is, I forgot to write it, but Z is the usual matrix Pauli Z operator that we had before. Okay, and now, so this Z1, Z2, this is exactly an example of this independent observable. So what that means is that Alice and Bob make a measurement, and each of their observables are Z. Okay. And basically, you have to work out what the expectation value of that operator here is. Okay. And I'll give you a completely general state here. Okay, so this is how you work it out. So of course, as usual, average of Z1, Z2 is just that. Okay. And so the first thing that we can do is just work out what Z1, Z2 times this state here is. And the way that we do that is, well, you can do it sort of part by part if you like. So let me sort of write it out for you. Okay, so we're trying to work out what Z1, Z2 of the state psi is, and yeah, okay. So, okay, cool. Let me write it out. A00. Okay. So, well, this basically what's going to happen is, oh, sorry, maybe I should have written this as Alice and Bob. Anyway, this is on Alice's side and this is on Bob's side. So basically, whenever I write this state like 0, 0, first one is Alice's qubit and the second one is Bob's. Okay. So when Z1, Z2 acts on 0, okay, well, let me just do one example here explicitly. So basically this Z2, which is Bob's operator, only acts on Bob's qubit because it's a measurement. Well, eventually, it's, how this is performed in practice is that actually Bob is performing a measurement on his qubit and Alice is performing measurement on her qubit. And so we know from over here that Z acting on 0 is 0, and Z acting on 1 is -1. Okay. So Z2 acts on 0, so from that formula, we know that it just gives just a plus sign here, right? So this one is that. And then Z1 acting on 1 also is plus, so this term is just 0, 0. We can do another term up here, Z1, Z2, say acting on 1, 0. So Z2 acting on 0 doesn't do anything. Z1 acting on the 1 gives a minus sign. So it gives minus 1, 0. So you can see that basically what the Z does is, well, obviously what Z does is to pull out a minus sign here, right? If it's 1. But because it's the product of two Z's, the terms that actually get a minus sign are only this one and this one, because so there's 1 here, right? So that'll contribute a minus sign. This term is going to be both the Z's are going to give a minus sign. So that's why this one ends up being plus, as you can see on the slide here. Make sense?
What does the double 0 in the Ken notation mean again? I kind of forgot what.
So 0, 0 basically means, so sorry, I'm kind of swapping notations, but maybe just to be consistent for this board. 0, 0 means, say, let's call this one Alice. Alice's qubit is 0, Bob's qubit is 0. So, okay, maybe if I were to kind of write it out properly, because actually all these things, so there's a Z1, Z2 tensor product, so that's our operator, and our state, which has tensor product also. So these operators acting on these states, so basically this Z1 acts on only this one, Z2 only acts on this one, so this one is going to be Z1, whatever that thing is, and Z2 like this. So these ones you know how to work out from here, and so so in this case it'll be 0, 0. So maybe that's clearer for you to see the structure.
And can you write it in matrix form?
Okay. So, if we want to write it in matrix form, then, okay, so firstly, for the single systems, sorry, I'll move around. It's 1, 0, and 0, 1, right? Okay, so we have to kind of establish a sort of a convention for the composite system. So for the composite system, let's because it's a 4-dimensional space, because it's Alice has a 2-dimensional space, Bob has 2-dimensional space, so combination is 4-dimensional. So we need to have a 4-dimensional vector here. So those are our vectors, and so our state, firstly, which is written up there, is just this: A00, A01, A10, A11. Okay, so that's our state. So now we need to, if we want to do this entirely in matrix form, so this is where it gets a little bit messy. But what we want to do is to work out what the 4x4 matrix of that thing there is. And what's the best way to do this? Yeah.
So can we rewrite the matrix into 2x2 instead of a column vector? I can think of 2x2.
I think it's better not to do that, because, so for example, if you had 3 dimensions, if you had 3 particles, then what you're going to end up with is like 2 by 2 by 2. It's going to be like a cube or something. And I mean, you can always do anything, but I think it's always better to strictly view like states as being vectors. So whatever your, whenever you're dealing with a state, you always make it a vector, no matter what the length is.
So like a two-state, two-qubit system is actually equivalent to like a one-qubit, four-state system.
Yeah, it is. So actually, there's no real sort of difference, quantum mechanically speaking, between the two, but often it makes a difference in terms of, because physically they originate from two particles and they might be in two different locations, for example, right? So because somehow physically, when you're doing measurement or doing anything, then you are actually kind of accessing sort of some part of this four-dimensional space, right? So you're kind of always accessing kind of these, for example, here, if you've got 0, 0, 1, 0, then whenever you say if Bob state is 0, then you're kind of only dealing with this element and this element, right? So you sort of kind of, what your physicality is sort of influencing, the kind of operations that you end up doing. So that's why it's a little bit, in principle there's no difference, but often practically or, operationally it can actually make a difference. Okay, so, right, so for this operator here, operators are always written as matrices. So what we want to do here is essentially we want to do the tensor product of this. So essentially we want to make a 4 by 4 matrix out of this two 2 by 2 matrices. And so this one, so our convention is that, okay, so this is our state 0, this is 1, this is state 0, this is 1, this is state 0, this is 1, this is state 0, this is 1, right? Okay, so when we do this tensor product of two matrices, we do something a lot like what we did with the vectors, where we have to sort of find every kind of combination of terms and then multiply them all together. So, for example, the matrix element for, so there's going to be like 4 combinations of columns, because you can have 0, 0, 0, 1, 1, 0, 1, 1, right? And there's going to be 4 combinations of rows, because you can also have 0, 0, 0, 1, 1, 0, 1, 1. Okay, so this is basically how you're going to end up with a 4 by 4 matrix. Like this. So if we want to get the matrix element of, say, 0, 0, what we do is we go, okay, so column is 0, 0, and then the row is 0, 0, so it's basically this one times this one. That's 1. Right? So the 0, 1, 0, 0, 1, so it's going to be 0, 1, and then 0, 0, 0, confusing myself here. 0, 1, okay, so basically 0, okay, or maybe the first qubit is 0, 0, so this one, 0, 0, this is 1, and then second one is 1 and 0, so it's 1 times 0, or this one is 0. Okay, so I don't know. I find actually this more confusing than the first one, but anyway. Anyway, so what you can do is continue on, and what you'll find is that actually all the off diagonals will be 0. Oops. And so here, to get this element, it's going to be 0, 0. So that element multiplied by 1, 1. So it's minus 1. So it'll be 1 times minus 1. It'll be minus 1. This one is going to be 1, 1. So it's going to be minus 1 times 0, 0. This is 1. This is minus 1. This is going to be 1, 1 and 1, 1. So it's going to be this one times this one. So that's plus 1. Okay. And then, so now that we've got our matrix, we've converted everything into the 4-dimensional space, and now we can just relax and just do matrix multiplication. So basically what we're going to be doing is, why don't we do it in parts? So let's multiply Z1, Z2, this matrix with this state. So take this state, multiply it by this matrix, and I think you can see just from, because you have this, and it's just elements that are along the diagonal minus 1s in the middle. So you can see that this one is going to be like this, yeah. Just took that state, multiplied by that matrix, and you get minus signs like this. And the thing that we're after is this one multiplied by the conjugate vector of that one. A00 star, A01 star, A10 star, A11 star, multiplied by A00 minus 01 minus 10. Do that matrix multiplication, and we get A00 minus A01 minus A10 plus A11. Which is of course the same answer as up here. Yeah, I find this one much easier actually than this one, basically because somehow, you know, here you got to work out the matrix for starters. That's
I think the transform from the the qubit state to the vector is kind of
yeah. Yes, exactly. Yeah. Whereas somehow over here with the kind of this operator and the brackets, it's, you know, working out each one of these is kind of pretty obvious, because essentially you just follow the rule that each operator acts on its own one, right? Because they're physically sort of separate. Okay. So that's one example. Here's another example, but with x, right? So remember our matrix, Pauli matrix X was this guy, and so basically what X does is to flip the spin. Right. So, if we want to calculate the expectation value of x1, x2, then what we do is, so let's just go through the same thing. So we apply x1, x2 to this state, to the original state, And so, fine to rub this out? Yeah. Okay. Right, so let's change this example to x1, x2. So as before, so x1, x2, let's evaluate just this term because all these things are linear, so these are constants. That's an operator, that's a vector, that's just a constant. You don't have to worry about the constant too much. So let's just work out the hard part, which is the matrix times vector. So perhaps maybe it's best to explicitly write this. So x1, x2 actually means x1 times x2 tensor product. And 0, 0 actually means 0 tensor product 0. So this is first analysis system, Bob's system. So x1, so this means that you just act the operator separately on each of its corresponding subsystem. And up there we've already worked out that x acting on 0 just flips the spin, x acting on 1 also flips it. So this is going to be 1 in subsystem 1. This is also 1 in subsystem 2. And then in my notation that just it means 1, 1. So basically if you've got like these two x's, what it does basically is just flip both of them at the same time. So 0, 0 becomes 1, 1. And you can probably see that 0, 1, if this was 0, 1, it flips both of them, so 0, 1 is going to become 1, 0. Because it flips both of them. Okay, so this is why, so in the third line here, so this term with the A0 coefficient, the state is flipped, so it becomes 1, 1. 0, 1, that A0, 1 term, state is flipped, becomes 1, 0. A1, 0, state is flipped, oops, missed a cat here. And A1, 1 becomes 0, 0. And then once you've got that state, you just do the expectation value formula. So you look at the original state, but the conjugate vector version of that. So it's, sorry, I did flip the vectors to be the conjugate. So a few typos here because I didn't have these last year. And so, yeah, so this should be all conjugate vectors as well. The conjugate of the coefficients are there, but sorry, I didn't flip the vectors. And here is this state here. So using the orthogonality, only these terms that are the same survive, right? So in principle, you've got 16 terms here because you got first bracket has 4 terms, second bracket has 4, so 4 times 4. In principle, there's 16, but only 4 survive because say 1, 1 overlap with 1, 1. That's 1, but all these other 3 and 0. And so the only terms that you get that survive in the 16 terms here are 4 terms. And first term is A00, A11 star, then second term is A01 and A10 star, this term, and this term, and this term.
Professor White, why should we use the bracket? I mean the,
Here,
yeah,
typo.
it should be, okay.
Yeah, typo, yeah. Yeah. So that should be all conjugate vectors. So these should be all pointing that way. Okay, and you could do it also matrix version as well. Well, okay, we can just sort of sketch it if you like. Okay. So let's kind of cheat and modify whatever I've got here. So let's change the matrices. So x1, x2. So our matrices are 0, 1, 1, 0, 0, 1, 1, 0. Okay. So this term is 0, 0, 0, 0. So multiply those two together. This term is 0, 0, and 1, 0, 0, 0, and 1, 0. So this term is 1, 0, and 0, 0. So this is 0, and this term is 1, 1, and 0, 0. So it's these two terms. Oh no, yeah. This term and this term, one times 1. And so likewise, what you should find is that it's a matrix that looks like this. And then so if you do the matrix multiplication, you multiply this onto this matrix, then the first term will be A11. Second term will be A10. Third term will be A01. Fourth term will be A00. So all that's changed here here A11, A10, A01, A00. And if you do that matrix multiplication, then I think you get exactly that. Okay, quiz time. So why don't you try evaluating this one using whichever method you like. Yep, 1. Yeah, that's correct. Danny, did you get 1?
No.
No. Okay. Okay, so x1, z2 expectation value is of course x1. Okay, you can write tensor product like so. And so let's first work out what x1, z2 acting on this state 0, 1 plus, sorry, 1, 0 plus 0, 0 is. So firstly, let's act Z2 on the second qubit here, both of them. And we know from over here that Z acting on 0 always gives just the state 0. So what we should get after acting on that is just the same, because they're both 0. And x, as we saw up there, actually just flips the spin, right? So, and it flips the first spin. So the result of this should be 0, 0 plus 1, 0. Okay. And now we can, so we already worked out what the result of this is. So x1, z2 psi. So this bit, that's just exactly what we worked out. We take the conjugate vector of the original state. So we pointed in the right direction this time. 1, 0, 0, 0, 0, 0. Okay, and then we can just multiply this whole thing out. And so the only terms that survive because of orthogonality are the ones that are the same. So only that term and this term survive. So the two factors of 1 over root 2 give a half. And there's only two terms in there that give 1. And so that's 1.
Question.
Yep.
For the matrix method, if we use, what would the vector phi be? Is it a 4-dimensional vector?
So 5 or what?
Oh wait, how did you?
Oh, psi, yes, psi, yeah.
Oh, yeah, I'm confused.
Yeah, no, for the psi,
Is it just plus like the 1,
Yeah.
0, 1, 0, like a 4?
Yeah. So the state psi, so you always have to establish some convention for the matrices. And actually, you don't have to choose this convention, 0, 0, 0, 1, 1, 0. You could choose any scrambled convention and it's going to be always fine. But, this is a good choice because that's sort of the binary sequence, right? So we've got a term on the 0, 0 and the 1, 0. So according to our convention here, that's the first one and the third one. So it's going to be that, and then there's a factor of 1 over root 2.
Yeah, but then I get confused when I try to do the multiplication on the like this is its conjugate is 1 by 4.
4 by 1,
4
yeah.
by 1, yeah, 4 by 1.
Yeah.
4 by 1 matrix, and then I have to multiply it by a 2 by 2 matrix, which is like x.
No. So this thing in the middle, this x1, tensor product Z2, this is a 4 by 4. So all these things have dimension 4. So here, remember we worked out what the matrix of the operator was, right? So x1 times z2, this is also a 4 by 4 matrix. And so you would need to work out what that 4 by 4 is. And, well, yeah, you'd have to sort of go through this procedure in general. It's a little bit messy, but it will be something like, so this is why I prefer to use the other method, because so this thing should be so again you go, so first term is basically multiplying these two, 0, 0. This term is 0, 0 and 1, 0. This term, third term is, I think this should be, yeah, this one and this one. Fourth term should be the other pair. So it should be like that.
Oh,
Yeah.
so yeah, we worked out all of that.
Yeah, so we worked out all that.
Yeah.
And, well, okay, just from the structure of this matrix, let's see, so I think, so the other one should be,
It's
yeah.
very easy to
Yeah, so
come
I think,
up with the wrong.
yeah,
It's all zero.
yeah, so, yeah, this is why I think it's better, in fact, in order to get this matrix, in fact, I'm using the other method to get to work out what the matrix elements are. So
Maybe the matrix method isn't a very good method.
that's what I think. Yes. Yeah, that's what I think for. But I mean, actually, when you do things numerically, you sort of have to do it more or less like this, because well, you know, computers work better with matrices and vectors rather than some kind of operators. Like, it's harder to code in operators, right? So often you do end up doing this, and in fact, I'm always very careful that I don't mess up the ordering of this matrix. Okay, so hold on, let me just finish off writing this thing. So what we should get is, I think we should get minus 1 here, and the minus 1 here. Yeah, I think that should be right. I think the matrix should look like this. Yeah. You know, maybe for people that are more used to the matrix method, I think another way to do it is to kind of think of it in terms of submatrices. So you notice that actually this matrix here is actually this one, right? And then this matrix is this one. And so I think it should be something like, essentially if you multiply these matrices by these coefficients, like, and then you have the 0 submatrix, and then this matrix multiplied by 1 gives that, and so forth. I think that also works, but you'll have to work out exactly how whether that works. But I mean, the method which I was doing it element by element, essentially to get the first row, it's sort of like multiply these two numbers, these two numbers, these two numbers, these two numbers, that gives the first row. And I think the second row should be, so it's 0, 0, and then 0, 1, right? So yeah, so it should be something like this one, this one, this one, this one to get the second row. And then I think third row would be this one, yeah, this one, this one, this one, this one. Fourth row should be this one, this one, this one, this one, right? So we can go through element by element. questions on this one? Okay, but I think it's good we did that in a bit of detail because it seems like it's. Yeah, I think I remember actually last year people were confused on this point too. Let's see how much more to go. Well, yeah, okay. Maybe we don't have to finish this one for the before the midterm, so we can leave like the whole of the next lecture for revision. So maybe you can come back with parts that you want to ask about. But yeah. Yeah, okay. I think we should just leave it there. Actually, it's a good place to stop.
I always thought there was a scheme of the clocks like in the front and in the back of the classroom because the front one is always a little bit faster.
All right.
And all the classrooms we
okay.
Yeah.
Yeah. Yes. So the lecturer thinks he's got more time. Okay. Okay, we'll leave it there.